Okay, this is the video for differential equations second day demos for the OCTAVE programming unit. In the last video, we talked about how to kind of the structure of using the GUI graphic user interface integrated development environment for OCTAVE. Then we looked at three examples, including a first order, a second order, which required us to use a system. And then we did another second order of a mass spring system where we could adjust some things to explore the beat phenomenon and resonance. What we're going to do today is another example. This one is going to be a system of differential equations, like an outright system of first order differential equations, but one that's a little beyond what we can do in the class. This is for predator-prey. And if you've been wondering, hey, they talked about this in Calc 1, but we never did talk about it in differential equations, we can talk about it now. So you probably were introduced to predator-prey systems back in Calc 2, and there are manual methods, but they involve some kind of unusual tricks. But the good news is that we can set this up as a system of nonlinear first-order differential equations, which is something OCTAVE can model. So we'll take a look at two examples here today and explore this. So first, let's take a look at an example involving two populations. Foxes, which are predators, and rabbits, which are prey. So foxes hunt rabbits, and rabbits are the food supply for foxes. So let's make some assumptions and build up to these equations and show you how they would work. If there were no predators and there was ample plant food, not amply, there was ample plant food for the rabbits, then we can assume that the rabbit population would just grow without restriction. So that's the population growth model. This A is just a constant of proportionality. So the rate of change of rabbits, it grows depending on how many rabbits there are, right? And then let's make an assumption that if foxes eat only rabbits, then the foxes are going to fight over the current supply of rabbits as food. And at a particular time, since they're fighting over the available rabbits, the fox population will actually decline based on a rate proportional to the size of the fox population. So since rabbits are definitely going to be a limited resource, then if there are too many foxes, then there will be a decline in the number of foxes in the next time period because there's not enough rabbits to go around. So basically, the more foxes there are, right, the more negative the decline of fox population will be because they're fighting for each other. They're fighting each other for the limited rabbit population to eat. So this is a negative constant, B. And B is just another constant of proportionality. Too many foxes, fox population declines faster because there's not enough rabbits to supply food. Basically, that's the assumption for that. And then if you bring these two populations, these species together in the same ecosystem, we could assume that the species encounter each other at a rate that's proportional to the size of the two populations. So if either population is larger, then the number of encounters goes up. So if we just take the number of rabbits R times the number of foxes F in the product, when that product is larger, either due to rabbits being high or foxes or both, the larger that product is, the more times they encounter each other. Right? Since an encounter is beneficial for foxes because it gives them food, but it's detrimental to rabbits because they get eaten, we can combine all these ideas together with this system. We could say the rate of change of the rabbits over time is AR, which means the more rabbits there are, the more rabbits they're producing because they breed very quickly, but minus some proportional constant times how many R times F is the number of encounters. So the more encounters there are, the faster we remove rabbits because they get eaten. On the other hand, the foxes, the more foxes they are, they're competing for a limited food source, the rabbits. So the more foxes there are, the faster fox populations decline. But that's balanced by the fact that every time there's an R times F encounter, then you're going to increase fox population, right? Because foxes go up when there's more food. So more food increases foxes, but the more foxes there are, that decreases the population. So this particular model, it's based on a whole lot of assumptions, but this A, B, and C, D, these are all constants. This particular is just sometimes referred to as a predator-prey system, and that particular set of assumptions that led to this are called the Lotka-Volterra equations. So this is a common way to model predator-prey. The problem with this is that you have first order differential equations, but because this r times f term, these are nonlinear. So all of our methods, we know how to solve systems of first order differential equations, but only when they're linear differential equations. Our methods right now with the psi and all that for the right-hand side, that stuff only works with linear, right? So we can't have these mixed terms like this, which is why we haven't seen this yet until right at the end of the course. But Octave can come to the rescue here. So we could include some initial values here, like and constants. Let's say, for example, that that the a constant is 10. This one's negative 0.01, negative 0.5, positive 0.01, something like that. Then we can also specify initial conditions, like maybe there's 90 rabbits initially and 100 foxes initially. And then we could build function files to build this. So let's actually do this in the editor. So I'm going to take one of the files from yesterday. Let's take the last one we did, which was the third function, and we'll make it a fourth example. So let me open up the example 3 and example 3, and we'll save these as example 4. So this will be example 4, and while I'm there, I'll change this to example 4. And then here we'll save this function as example 4 script. We'll change it to call example 4, and then we'll start modifying. All right, let's look at the differential equation function first. All right, so we have a true system now, not a second order differential equation that's being modeled as a system. Now we have an actual system, and we're still going to use the same kind of structure, right? This x is going to represent an array, except now it's not an array of the equation and the derivative. Now it's an array of one variable and the other variable. So let's use the first column to represent the rabbits differential equation, and the second one, f, to represent the foxes. So that means r is the first value, f is the second value, right? And I could still call this t, right? It's time, everything's over time, and this x variable here is an array for rabbits and foxes together. Okay, but now I'm going to specify not that this is the differential equation of this. We're going to actually specify both differential equations themselves. So the way they're entered is as a matrix like this, or as an array separated by a semicolon. But we just entered the first differential equation before the semicolon and the second differential equation afterwards. So let me go through that. This first differential equation is for rabbits. So it's 10 times rabbits, so 10 times. Now for the rabbits, I'm just going to enter x1 because the first column here of my x array is the rabbit value. That's the equation for rabbits, so this is the rabbit. And then minus 0.01 times rabbits, which is x1, times foxes, which is x2, right? The array, but the second column, which is the foxes. Okay, so that's the first differential equation. We'll put a semicolon here to separate it from the second differential equation. Now we're going to enter this negative 0.5f plus 0.01 rf after the break here. So we've got negative 0.5 times foxes, which is x2, plus 0.01 times rabbits, which is x1, times foxes, which is x2. Okay. So hopefully you can kind of see the pattern of how this all works, right? Now our array is rabbits, foxes, rather than, y prime. It's just two y variables, the y variable for rabbits, the y variable for foxes. All right, so we'll save that, and then we'll move on to the script. And for the script, we're going to do a couple of different things here. So I've got my clear all, CLC, time range. Let's go to 0 to 20. That works out well for this problem. And then for our initial values, we have to put the initial values for the first column, which is the rabbits, which was 90. And for the second column, the initial value for the foxes, which is 100. Okay, we're calling the function here. And then let's do I'm going to label this with a comment here. This is time plots. Let's plot rabbits and foxes versus time. Okay, so in that case, I'm going to have two plots. I'm going to have two curves on my plot. I'll have t, x1, and b. That's going to be for the rabbits versus time. And then maybe I would want the foxes versus time. So t, and then the second one. So x parentheses colon comma 2 gives me the second column's values, all the values in column 2. That's the foxes. And then let's use red for foxes because they're predators. So the y label is going to be populations because it's 2 populations. And then this is just going to be time. I'll not specify that. And then for the legends, the first one, we're going to call that rabbits. Right. The second one is going to be foxes. And then in the Northeast, we'll put a legend. Let's leave the box on this time. All right, so let's go ahead and save that and plot that and see what happens. So if I save that, if I go to the script file and execute, oh, there it is. Okay. So what's going on here? Let's see if I can make that a little bigger so we can look at that. All right. So in blue, we have the rabbit population, and in red, we have the foxes population. So what's happening is over time, right, we started out with 90 rabbits and 100 foxes. And at first, the rabbits kind of breed, which is good. As they breed, there's more foxes. They're eating all those rabbits, so they go crazy. But at a certain point, there's so many foxes that they start eating the rabbits, and the rabbit population drops again to near zero, right? And then at a certain point, right, the foxes lose their food supply, so they stop, they die out because the rabbits are gone, and pretty soon the rabbit population recovers. And as they do, the fox population rises to join it. So there's a cyclic behavior here, right, that goes like this. Interesting. So that's one way we can plot this. We could plot one of these populations or both of these populations versus time in 2 time plots. But because we have 2 variables, we could do a 2D phase diagram or a 2D phase portrait if we wanted to. So that's what the second part of this is doing. I'm going to comment out this. I'll just leave it there so I can go back and forth. Let's comment this out. And then let's put a different plot in. Let's do a phase diagram that shows foxes versus rabbits. Now, this is just a comment. I'm just labeling here. But what I'm going to put here is plot. I want to do instead of having time on the x-axis, I want to use rabbits on the x-axis and foxes on the y-axis. So that would be plot x colon 1. And then let's put the values, all the values in column 2, which is the rabbits or foxes. And maybe I'll make the curve blue. Okay. And then I could, I guess, label this. Let's make a y label foxes and x label rabbits. Okay, and then let's save that and run it. Let me bring up my window here. So if I run this now, I get a phase diagram. So what this now shows is rabbits are the x variable, foxes are the y variable, and you can see how this is cycling. It's hard to see, but there's a curve here. So it starts out here at 90 rabbits, 100 foxes, and it goes like this, right? Everything increases for a while, but then the fox population keeps going up and the rabbit population keeps going down until finally there's so few rabbits that the fox population drops, and then the rabbits recover, so we go back around again and back around again, and it's just cycling. So it never really reaches any kind of equilibrium point here, right? There's no stable values. It's just going to oscillate around like this. All right. So this is called a phase diagram or a 2D phase portrait, and kind of interesting. So that's how we can use OCTAVE to analyze a predator-prey situation. Let's take a look at a more complicated one. Let's add in a second prey species. So let's say that in addition to rabbits, there's turkeys in this forest, and foxes eat both rabbits and turkeys. And then let's make this really complicated. Let's say that the turkeys and the rabbits don't interact with each other, right? But both the turkeys and the rabbits can't just grow without bound. They're actually limited by their food sources, which are the plants. So instead of just modeling them as like back here where we model these let me go back to here. When we model these as directly proportional to the population, let's replace this with a logistics model. So if we use a logistic model for the for this rabbit population would be instead of just a constant times r, right? It'll be a something minus something r times r. So it ends up being a second order nonlinear uh, because it's a logistic model. And then we still have the population being reduced by the encounters between the rabbits and the foxes. And then we would have a similar equation for the turkeys. Let's make the constants a little different. This would have to come from some sort of experimentation. But they also, now this time we'll use capital T for the turkeys, different constants here. And they also, population of turkeys are reduced when we have turkey fox encounters. There's no R times T terms though, because it doesn't matter if the turkeys encounter the rabbits. They don't eat each other and they don't, nothing happens. But the foxes, right, are they're negatively affected by other foxes because they're competing with each other for the food source, but they're increased by both rabbit fox encounters and turkey fox encounters. And then maybe by making this 0.02, we're saying that their foxes are twice as likely to eat a turkey in an encounter than they are to eat a rabbit in an encounter. For some reason, they like turkeys better. They're bigger, I guess. I don't know. And then we would also have to specify initial condition for the turkeys. All right, so we can make this very complicated, and this is well beyond what we could do using manual methods that we've learned in this introductory class that we've taken here. But Octave can handle this. So let's go ahead and save this as a new set of files. So I'll go here to the function file, save this again as a new file. Let's do 5. All right, and I'll change this to 5. And then let's go over here to the script file and save that as another file. Here, we'll make it call the 5 function. All right. And then let's go start replacing things. So before we had equations just for rabbit and fox. Now we've got a rabbit, a turkey, and a fox. So we have to decide the order. Let's make this the rabbit's the first column, turkey's the second column, fox is the third column, just like they are here. And that means I have 3 equations to enter, right? These 3 equations, and they're more complicated. But every time I encounter a rabbit, it's going to be column 1, a turkey, it's column 2, and a fox is column 3. Right, so this is what I would need to enter. So let me go back to my function and we'll set up the differential equation. Same setup, he's the input variable, vector x is the output variable, and this is going to be a big long thing to enter here. So for the rabbit equation, it's going to be 0.01 times parentheses 100 minus the rabbits, which is x1, close parentheses, times rabbits again, so x1 again, and then minus 0.01 times rabbits, which is x1, times foxes, which is x3. Semicolon, that's the end of that differential equation. Now let's do the turkey one. So that's going to be 0.04 times parentheses 80 minus the turkeys, which is x2, parentheses, and then times turkeys again, which is x2, right? And then minus 0.03 times turkeys, which is x2, times foxes, which is x3, semicolon for the end of the turkeys one. And then we can enter this equation here for the foxes. So over here, we're going to have negative 0.5 times the foxes, which is x3, and then plus 0.01 times the rabbits, which is x1, times the foxes, which is x3, and then plus 0.02 times the turkeys, which is x2, times the foxes, which is x3. All right, so that whole big thing there is the differential equation, and we'll save that. Differential equation system. Okay, we can go over here to the script file, and we're going to do kind of like what we did before, but let me just, let's do a time plot first. Put all 3 of these on one. So we'll have plot, we're going to have X label, Y label, and legend. So the plot this time is going to be one thing for the first thing, which was rabbits, right? We have the second thing, but the second thing now is going to be turkeys. So let me change this to turkeys. And let's change that one to green. And then let's add a third plot here, T versus X third column, all the values in the third column. and we'll make that one red for the foxes. So the foxes will still be red. That means I'm going to have another thing here, populations versus time, but now we have 3 curves, rabbits, turkeys, foxes in order, and we'll have a legend in the top. All right, let's save that and give that one a try. Okay, so if I run it, it didn't change over here, which means probably there's an error. Let's see if I can figure out what happened. If I go over here to the command window. Plot, error near the end here. It didn't like this by the time we got to the end. Oh, there's a stray. Looks to me like, okay, I've got this. See how there's the quote marks here, but I've got this extra quote mark here. I don't think, I think the error is actually there. So at least it's in this area. Let's go to the script. And I think the problem is this. That needs to be a variable. Right, now let's save it and try it again. Still didn't run. So let's go back over here. Let's see, starting step side, adding a column, out of bounds. Error 3 is out of bounds too, okay? Let's see. So a lot of times when you do this, you have to, oh, I didn't give initial values. That's another thing. So I didn't give an initial value for the third one here. I can see another problem that I need to add the initial value for turkeys. That could cause potentially something to go out of bounds if you don't specify an initial value. Let's see if that fixes it. And you're going to have to debug. This is totally normal, by the way, in computer programming to not get it right the first time and have to go back and try things. All right, this looks better. So let's take a look. All right, so versus time. It looks like just like before, right? We have some rabbits in blue, some turkeys in green, and some foxes. The foxes immediately start eating the rabbits and the turkeys, right? So their populations drop, and as they get too low, not quite zero, although the turkeys get almost to zero, right? The foxes prefer them, so they eat them at a higher rate than the rabbits. But eventually, the foxes population drops off because there's too many foxes competing for this limited resource. And at a certain point, these start to recover. And then the foxes go up again, but not as high. And so they kind of end up, now this one, they actually end up at 2 values here. In fact, if I put my cursor over here, I can kind of see that it looks like the foxes end up around, let's see, the Y value here is about 84. So it looks like this ecosystem would be stable with 84 foxes in it, because there's just the right balance between food and predators and prey. And then the green value is a little higher here, maybe around 17 or 18 and 16, maybe 17 and 16, 17 turkeys, 16 rabbits, and 84 foxes or so, somewhere around there is the stable situation. All right, we could also do phase diagrams, like we could do foxes versus rabbits. So let me comment out these over here. And let's uncomment our phase plot, phase diagram. If we do 1 versus 2, that's going to be rabbits versus turkeys. So let me change this to 3 so that it's foxes versus rabbits. And then if I run that, yeah, that's interesting. So we can see that it starts out with 90 rabbits and 100 foxes, right? The rabbit population decreases, the foxes population goes up. But then as the rabbits get low enough, eventually the fox population drops again. The rabbits start to recover, and then they kind of spiral in eventually to an equilibrium point here, where we have just under 20 rabbits and around 80-ish, 84 or 85 foxes. So there's that same equilibrium point. This is what it looks like on a phase diagram. And we wouldn't just have to do foxes versus rabbits. We could do another one of these. Let's do foxes versus turkeys. So if we want to do foxes versus turkeys, then we would do 2. So we could keep foxes as the Y variable, but change turkeys as the X variable. And if we ran that, same kind of thing, right? The turkeys start out here. they rapidly decrease because we made the 0.02 multiplier twice as big. Foxes eat them twice as fast, so they drop really precipitously and get really low, right? At some point, the foxes, their food supply reduces, and then it recovers, and then it goes back down again, and finally ends up at equilibrium. And we could even do turkeys versus rabbits if we wanted to. Let's do that. So if we wanted to do rabbits versus turkeys, that would be 2 versus 1 here. So let's see, the y would be the turkeys in this arrangement, and the x would be the rabbits. Let's see what that looks like. Let me comment out this. If you don't comment this out, it'll always show the last one overwrites the previous ones, but I like to only keep one of them open at a time. All right, so yeah, sort of chaotic because we said that rabbits and turkeys don't interact with each other, and they don't directly, right? They don't eat each other. They're not dependent on each other as food sources, but they are linked because they're being eaten by foxes. So there's an inherent connection, a hidden connection that does cause there's a relationship of some kind between them, but not obvious. Okay, and then we could do a phase diagram of all three, right? We have three populations, so it's actually possible to do a three-dimensional phase diagram. We didn't ever try to do this in by hand, of course, but you could do rabbits versus turkeys versus foxes all on the same plot. It's just now going to be a three-dimensional plot. So what you have to do is you have to change this to be plot 3, and then you've got x, y, and z. So we've got an x for the foxes as well. And then I'm going to add on another label here. It doesn't matter the ordering here. This one's going to be the foxes. Okay, so what does that look like? Well, it'll actually produce a three-dimensional graph. So we've got rabbits on the x-axis here, turkeys on the y-axis, foxes. It doesn't show our normal convention. Normally we have x's down and y this way, but you can kind of see that it starts out at some particular point here of rabbits. There's like, what was it, 90 rabbits, 100 or 80 turkeys, and 100 foxes. And then this is moving through 3D space to a equilibrium point that specifies the rabbit and the turkey and the fox value. So that this is called a 3D phase diagram or a 3D phase. All right, so really interesting things. All right, that's where we're going to leave that at this point. This is all the things that come out. So you can kind of get an impression for how powerful this is. And now in class, I'm going to give you a couple other things to work on. We're going to have you redo one of the mass spring problems with different cases as homework problems. We did that, I think, the first night. I'm going to give you another thing to try. It's called, well, we'll talk about it in class. So look for either Schoology or in class to learn how you can explore this for the nerd prey, but it's something different. It's a forensics example.